Hello, everyone. This is Gary Rosenfield, and welcome to the virtual Spaceport America Cup. I'm hoping that maybe next year we can do these things in person, like we've done before. But in the meantime, I'm happy to give a little talk on the design, evolution, and production of long-burning hobby rocket motors. And there's going to be a lot of history in here. Hopefully, you'll enjoy this. Just give you a little idea of my background. I know some of you know about me, but probably a lot don't. I got into hobby rocketry in 1969 and quickly went through the scope of the hobby at the time, including Estes and FSI motors. And some of you may not even know what FSI was. It was Flight Systems. They made a larger version of Estes motors, up to F motors. And then about 1970, 71, a company called Enerjet came along, and they were a subsidiary of Century Engineering Company, which was a major competitor to Estes. They were in business from around 1970 to 1974. I flew a lot of their motors. I clustered them, staged them, even a 3-stage rocket with them. And as I've said before, I credit the Enerjet line with my career in rocketry, because it just sparked my imagination far beyond what was available with the black powder motors. So I became interested in making motors, and in 1973 I built and fired my first successful composite propellant motor. And in 1974 was when Enerjet went out of business. I could see there was a business opportunity there. So I started a company called Composite Dynamics at that time. That was one of the first two companies after Enerjet. The other, Sonic Rocket Systems, Mark Maley in Mount Lake Terrace, Washington, started that one. We were good friends. Our companies going at the same time. Between 1976 and 1980, I was in the Air Force. I was an imagery interpreter, had nothing to do with rocketry, but I was involved. And, but at the same time, on my spare time, I was running Composite Dynamics with a business partner who I'll discuss later on. In 1980, after I got out of the Air Force, I went to work for the Burmite division of Whitaker. They were a manufacturer of munitions for government, including the Sidewinder missile. And then in 1980, from 1982 to 1984, I was a manufacturing engineer for Aerojet Tactical Systems. You've probably heard of them. They made everything from the Minuteman second stage to another version of Sidewinder, Harpoon, Missile X second stage, Hawk, Standard Missile, stuff like that. So I got to work on manufacturing issues for those motors. In 1982, I founded Aerotech, and then in 1985, I founded Industrial Solid Propulsion with Dan Meyer for commercial applications. And then RCS is the parent company right now of Aerotech, ISP, and Quest. That was founded in 1985, and we were one of the first commercial experimental or research rocketry suppliers. I've been a member of the National Association of Rocketry since 1971. I was a board member between 91 and 94, and I was awarded the Howard Galloway Space Modeling Award in 1989 for the development of the modern composite propellant hobby rocket motor. I've been involved in Tripoli since it became a national organization. Was a board member from 1989 to 1995, and also from 2017 to the present. And in 2001, I was awarded the Lifetime Membership Award for contributions to the hobby. And also since 1984, I've been involved in the NFPA Pyrotechnics Committee as a manufacturer member representing my business. And in that period of time, we have seen all kinds of improvements and technological advances in the hobby, and those have been incorporated into the fire codes that are now adopted by lots of different, state and local, what they call authorities having jurisdiction, fire marshals, and so on. All right, so as a matter of introduction, this presentation will deal with long burning hobby rocket motors used in model, high power, mid power, and high power hobby rocketry. Now, in professional rocketry, long burning motors are a natural result of the large size and propellant web thickness in core burning designs. There's a scale up factor involved there. But because of the relative small size of hobby rocket motors, special propellants, materials, and designs had to be devised to produce the burn times exceeding just a few seconds. And to begin, we'll discuss the early history and developmental evolution of longer burning motors for hobby rocket applications. So the first hobby rocket motors were end burning designs using black powder, such as the Flight Systems F7 shown in the picture. This was a long, roughly a, 27 millimeter diameter by 5 or 6 inch long black powder motor. Now, black powder has a relatively fast burning rate, which is about 0.7 inches a second at low pressures. And it's well suited to end burning motor designs, as the end burning grain can produce sufficient mass flow for practical thrust levels. And a small dimple or a particle core is formed in the nozzle end of the propellant grain, which creates an initial thrust spike and helps get the pad and accelerate it to a sufficient velocity to impart as it takes off the launch pad. Now, early long burning black powder model rocket motors, such as the FSI F7, were modified end burners with above average burn times. And in the case of the F7 was up to 9 seconds. Now, when ammonium perchloride composite propellant, or APCP motors, first arrived on the scene in the late 60s and 70s, they were all core burners with burn times of less than 2 seconds. The core burning geometry was a result of the much slower burn rate, which was generally only 0.15 to 0.25 inches a second, of composites compared to black powder propellant. Now, composites generally needed more surface area to generate the same mass flow rate as black powder, though the propellant efficiency of composites could be 2 to 3 times higher on a per weight basis, but the propellant's generally lower density. Now, as core burners, the relatively shallow web thickness, which is the distance between the core and the case wall, and in the case of these Enerjets was about 1/4 of an inch or less, that would result in a relatively short burn time. And those were the Enerjet E24, F52, and in the lower right there's a picture of an Enerjet E24 firing. You can see the mock diamonds. Those all burned for less than 2 seconds. Now, referring back to composite, and John was a senior engineer at Hughes Aircraft in El Segundo, California. And he had access to materials and equipment that I didn't. He started experimenting with a number of exotic motor designs, including end burning composites. And the first end burning composite motor I ever saw was a 2-inch motor, 2-inch diameter motor with a graphite nozzle that John static fired in his backyard. I don't remember the exact burn time, but it was truly amazing, and it really sparked my imagination and specifically got me interested in pursuing that type of motor design. And sometime after that, John started producing 29 millimeter versions of his end burning motor designs. Now, we were using these thin wall or 32nd inch wall fiberglass casings for all the regular Composite Dynamics motors. And just so you know, we had for example, one was an E20. It was the first 24 millimeter full E composite motor, the same diameter and length as an Estes D motor. But John would use rolled up silicone and various gasket materials, probably even asbestos, or in some cases he would machine down some 29 millimeter paper phenolic casing material, and he would use that for a liner, because you just can't put long burning motors, generally speaking, into especially a thin wall fiberglass casing and expect it to last very long. Now, John always cast the propellant directly into the liner of the gasket material. And what's common now is this casting into paper tubes, and I developed that method sometime after that, way back there in the 70s. The rolled up liners made of gasket materials had mixed results. It became clear to me that the best liners were the machined phenolic tubes. Now, at one point, John had produced a couple of 29 millimeter G12 size end burners. They were about 5 inches long or so. And he used thicker wall, which was like a 1/16 of an inch wall, 29 millimeter fiberglass casing with no liner. And during NARAM 20, which was what, 40 some odd years ago, Mark Maley, Mark Maley, who was from Small Sounding Rocket Systems, Roger Johnson, who was an early proponent of composite motors, and I flew one at Anaheim Stadium in California. Try to get away with that now, by the way, in an Enerjet style 1340 rocket, which is basically minimum diameter rocket, and it just disappeared. I had 2 of them. The other one was saved and donated to the Museum of Flight in Seattle. So someday you might see it there. John later produced a 29 millimeter E9 end burner motor for sale. And I had one of those and donated them to the Museum of Flight. Just as a note, that particular motor had no liner, and it got very, very hot. I wouldn't have run it any longer than it was running. So these motors really impressed me, and I became determined to produce similar versions of these of my own design. And shortly thereafter, I decided to leave the Composite Dynamics partnership, which at the time had 3 partners, and John and I had some personality differences, and also we differed in the direction of the company that we wanted to pursue. And so I sold my interest in the partnership at that time. So again, that paper casting tube technique was developed sometime while I was in the Air Force, but John dismissed the idea as having problems with accelerated aging. And that was one of the reasons I kind of left that partnership. Was I had some ideas that he didn't think were good. And, but I thought they probably would work. So I kept going on my own. But I got to thinking, why use a separate liner if you could make the case and liner out of the same material? So I started casting propellant grains in 1-inch OD paper tubes, and which basically were 24 millimeter motor mount tubes, and using a 16th inch wall 29 millimeter OD phenolic casing, which functioned as the case and liner combined. So the casing was strong enough to withstand the pressure, and phenolic ablates at a very low rate, which I can't remember whether they say it later or not, but it's around 0.003 of an inch a second. So you could literally burn away half the casing wall and still maintain some amount of integrity of the case. Anyway, it worked great. You got a benefit of the superior liner material with the simplicity of a one-piece case and liner design. Simplified the whole thing. Oh, that picture up in the upper right is just some very early production motors, F10 motors. There's a graphite nozzle that's held in there with a little mold, and then I would pour epoxy around those to hold them in place. Now, in 1981, I wrote a series of 3 articles for Jerry Irvine's California Rocketry magazine on motors of the 80s, and recently I got permission from Jerry to republish those or post those. So they're available on the RCS, rocketmotorparts.com website under documents or somewhere in there. If you search around, you'll find them. You can read them. Anyway, they dealt with topics such as history, the trending motor technologies at the time, and compared various grain designs and performance optimization. And the third article about performance optimization, I went into great detail into determining the type of thrust curve that was best for maximum altitude performance. The conclusion was that a thrust to weight ratio of about 2-to-1 would generate the highest altitude for a typical mid-power model rocket. Now, it turns out that you do that for too long and it's not really practical. But if in theory, if you run that on a computer and you plot the altitude versus burn time, you'll see that that's pretty close. But going through this exercise, supported and reinforced my interest in the long burning motor development, because I was kind of on an efficiency kick at that point. So let's look at some advantages and disadvantages of long burn versus short burn motors. Again, it's relative, but we're talking about, hobby rocket motors. So rockets powered by long burn motors generally achieve higher altitudes. So a motor with 1,000 Newton seconds that burns for 10 seconds will generally go higher than a 1,000 Newton second motor burns for 2 seconds. And there's generally lower acceleration and velocity, which means lighter weight airframe materials can be used. Motor chamber pressures can be lower, casings can be thinner and lighter weight. There's little or no aerodynamic heating on K-size motors and smaller, and I'll explain that a little bit later, I think. You can get a higher motor mass fraction because there's no core. Some of that's traded off in terms of your liner thickness, so you're going to lose some propellant with the thicker liner, but you'll make up for some of that with the core not having a core. Nozzle throat erosion can be very low depending on pressure and duration. We had a long time ago, Scott Pierce, when he was working for Aerotech back probably in the 80s or so, built an H5 motor. So this was like a 200 Newton second motor that burned for 40 seconds. And it ran at a fairly low pressure. It was low enough that after 40 seconds, there was no measurable erosion on the nozzle. And that was probably due to the char layer effect keeping up with the actual erosion. Now, the disadvantages of long burning motors would be, for example, the long duration motors require additional case insulation, which adds weight and reduces mass fraction. And total nozzle erosion might be higher depending on operating pressure and duration, opposed to a short burn motor. Case heating can quickly rise to unacceptable levels, meaning the motor will just get too hot for certification or cause damage to your airframe. Your specific impulse suffers if the chamber pressure is too low. Rockets may be subject to so-called gravity turning if the thrust duration is too long. In other words, they'll start arcing back to the ground under thrust. And they have limited weightlifting and payload capability. Pyrotechnic time delays are much more difficult to implement in a production environment as opposed to a core burning motor. Now let's take a look at moon burners. The moon burner was originally, the original concept, if we want to go back all the way, was about 1973. A fellow by the name of Rick Bennett developed a keyhole shaped offset port rocket motor design. That's shown in that little picture up in the upper right. Using composite propellant that was flown successfully a number of times at the Smoke Creek Desert in northern Nevada. And then in 1981, another fellow by the name of Bill Wood, who I knew really well, he kind of counseled me on when I went into the Air Force, because he'd been in the Air Force in Vietnam, and we spent many times together talking about things, rockets and Air Force and everything. He independently conceived of what is now called the moon burning grain design, using an offset cylindrical port. Now, Bill tested these motors at Smoke Creek launches. As I recall, it was in the early 80s out there. I was immediately impressed by the possibilities. And the original G30 or G25 Aerotech motors, which actually was the first Aerotech motor that was sold, was based on Bill's grain configuration and was the first motor, again, officially designed after leaving Composite Dynamics. There's your typical moon burning grain design. And this is part of these little illustrations come out of a paper, I think, that is, again, posted on the rocketmotorparts.com website that Bill wrote for presentation at a professional rocketry conference. You can see that paper if you want. So the original G30, the first Aerotech motor, used a phenolic case and a machined graphite nozzle. And it used what is now known as a form of the Aerotech classic propellant, which was basically just AP and HTPB binder with a little bit of carbon black, so no metals, and had a small core nearly completely offset to the edge of the casting tube. I left a small web between the core and the casting tube to provide a short initial thrust spike. And quantity of those were produced for, going back again, Jerry Irvine, and he sold them under, he called them Toy Rockets brand. Don't ask me why. And actually, a number of them were sold and flown at LDRS-1, the very first LDRS in Medina, Ohio. And there's a little thrust curve of it in the lower right there. So, you know, if you, there's something called the INTERNATS, which is international competition the NAR gets involved in every couple of years. And in the late 1970s, I began speaking with Bob Parks about long burning motors for their team for use in the FAI S8E radio controlled rocket glider event. And the conversations became the impetus for me to develop the Aerotech E6 24 millimeter motor, which became the first certified Aerotech motor in 1982 and the first certified long burning composite. E6 had a 40 Newton second total impulse and a 7-second burn time. And the US INTERNATS team won several awards in that event in 1983 using the E6. And there's just an interesting recollection by Bob Parks I solicited from him as, you know, for history's sake. But he said, at the beginning of a world championships, the teams submit all the motors they plan to use in the contest. The motors are impounded by the officials and given out to the contestants at the launch pad just before each flight. The officials will also pick a couple of motors at random from each batch submitted and fire them on a test stand to verify that the motors meet the rules for that event. Each team will generally have some people watching the testing. At that time, all the other countries had paper casing black powder E-motors for the event. The USA Aerotech E6 motors were really unique with the phenolic casings and graphite nozzles. They were also much smaller and lighter than the black powder motors. When they were ignited, they had the clear blue flame, no smoke, and nearly 8-second long, very smooth, sustained burn. Everyone's jaws dropped. And then the total impulse data came up. Both motors were about 39.5 Newton seconds. The limit was 40. And jaws really dropped. The weather conditions for the event were poor. Dark, overcast, cold, and windy, with pretty heavy rain for the last round. But the USA team swept the event with first place, Phil Barnes, second place, Karen Dillon, and third place, Bob Parks. Plus, of course, the team first place. The USA score was over double the second place Polish team. So interesting history for the first introduction of long burning composite motors at an international competitive event. So just looking at the E6 design, the original one used a machine graphite nozzle suspended in epoxy using silicone molds and a paper phenolic case. It had a rod and tube configuration on the end of the grain for the initial thrust spike, and it was created by a plug cutter tool. So if you go into a hardware store and look for a plug cutter, you'll see what that core looked like. The E6 was produced in 3 different delays and even a booster that could be used in a 2-stage rocket. The user would put a short piece of thermalite wick between the 2 motors to ignite the upper stage. And a customer by the name of Greg Smith flew his rocket called the Skint. He used 2 E6 motors staged as we just described. He flew it to an estimated 8,000 feet at Lucerne Dry Lake about 1982. And that's the photo of it taking off in the upper right. The lower right is an ad that we ran about that time with Greg's rocket, you know, highlighted there. That was in California, Jerry Irvine's California Rocketry magazine. Now the F10, which was the larger version of the E6, was actually my first design, ENDBURNING design, but was the second one to be certified. It's similar to the E6, but with a 29 millimeter phenolic casing. It had a larger graphite nozzle and the same rod and tube end configuration. 80 Newton seconds of total impulse with a burn time of about 8 seconds. And like the E6, custom silicone molds were made to position the graphite nozzle inserts within the aft bulkhead epoxy while it cured. And you can see that another picture of that little rack of motors there. They're produced like in batches of 40 or something like that at the time. And the epoxy for these motors had to be post-baked at 150 to 200 degrees to fully cure. because if you didn't, the hot graphite nozzle would just melt the epoxy and could get ejected. So by post baking them, it more fully cured them, and then the epoxy would just char and not melt. Other early end burners, for a short time in Sacramento between 1982 and 1984, I was making some G10 and G12 motors. These used a composite 2-layer case of a phenolic liner and a thin wall filament wound fiberglass outer shell overwrap. And they generally worked well, except occasionally the phenolic liner wasn't bonded well enough inside and would be ejected from the case during the burn. And also produced some D7s and some 18mm D2s and D3s. So I tried to explore like the whole model rocket range at that time with this configuration. Then we had a competitor. For a brief time in the early 80s, Irv Waite was who actually invented the Enerjets, and which were purchased by Centuri back in the around in the late 60s, early 70s when they were making them. But Irv Waite produced an E-class end burning motor. They were initially made for Reaction Technology Incorporated and sold under the trade name WIRLWInd. Yeah, that's the way it was spelled. But were later sold by North Coast Rocketry. They used a translucent 29mm fiberglass case, and I recall it was a thick wall case, and an end burning propellant grain based on potassium perchlorate. And they were about an E24 and only burned for about 2 seconds. Probable reason for that is potassium perchlorate propellants burn much faster than ammonium perchlorate. They were difficult to ignite and didn't sell very well, and I donated a sample to the Museum of Flight. And again, I solicited Chris PEARSON, who knew more about the WIRLWInd motors than anybody else, on his recollection of this. He said Irv Waite of RDC made those. Originally, they were made for Reaction Technology, Inc., which was J.P. O'Connor and Mark Weber down in Cincinnati, Ohio. After a short while, they decided they didn't want to sell them anymore and let us take them over. They were called WIRLWInd motors, and I believe they were a 40 Newton-second E24 motor. They indeed used potassium perchlorate as a fuel. They had a translucent fiberglass case, and you could see the case bonded propellant and a plenum chamber. I have no idea why the plenum was there, between the propellant surface and the nozzle. They were an end burning motor. They needed a special high energy igniter to get them started. Very slow startup. I remember advertising them as the first smoky composite motor, and they came out a bit before your White Lightning motors were released. I believe that we were selling them in the mid-80s when everyone was still on speaking terms with Weber. We never sold many. After a couple of years, we dropped them from the catalog. Nobody complained. Okay. All right. So, eventually we broke the long burning mode into high power rather than just model rockets. So when you go back through the history of the high power hobby, early high power rockets were built from simply larger versions of model rocket components, thin cardboard tubes, balsa fins, and nose cones. Why not, right? The high thrust motors would cause many of these rockets to shred during boost. So it became clear to me that long burn motors would be ideal for the early high power rockets. And this led to the design and manufacture of the 54mm I-65, J100, and J125 moon burning single-use motors. They were introduced at an early LDRS in Medina, Ohio, and they were a big hit. And the Lock Easy I-65, if you ever want to know where that name came from, was designed by Ron Schultz specifically for, you got it, the I-65. And by the late 80s, Aerotech developed the 98mm K125, L250, and M500 moon burners. So these are all basically the same motors, just longer. They were single grain, single use motors using Aerotech classic propellant, in other words, smokeless, in a phenolic casing that burned for up to 20 seconds. Aerotech attempted to fly an M500, so it was a 10,000 Newton-second motor burned for 20 seconds. In Jim Dunlap's upscale Enerjet Athena, that's in the picture there on the upper right, at one of the first LDRS in Hartselle, Colorado. But unfortunately, the M500 experienced a CATO and destroyed Jim's rocket. And then Scott Pierce, who we've referenced before with the with the H5 motor. He flew a K125 at El Dorado Dry Lake, and it was never recovered, just disappeared during the burn. The thick wall, large diameter phenolic casings were prone to weakness and variability, and that's a whole nother story. Okay, in the early 90s, Aerotech introduced the 54 millimeter K250, which was a long burning full K single use motor. The K250 used a modified version of the moon burning grain concept and combined a shallow C slot with a tapered version of what is now called a D grain. Kind of a very weird looking grain, but it worked. Burned for about 10 seconds and provided record-setting performance and lightweight rockets. And Ron Schultz's wife, Deb Schultz, flew one in a 54 millimeter laser lock to well over 20,000 feet of Black Rock. And I don't recall the exact altitudes, but I think I remember hearing about a 23 or 24,000 foot flight with this motor. It might not have been hers, but it was somebody else's. In the mid 90s, Aerotech introduced the J90, the K135, the K185, and the K270 54 millimeter RMS reload kits using White Lightning propellant. And instead of a circular core, they used a machined rectangular moon burning style or offset slot grain. It was for the purpose of manufacturing ease. And in 2007, the RMS 38360 I-49 end burner and the 38480 I-59 boost sustain motors were certified. So kind of pushing this to the limit is a picture of, I believe this is Kip DeGurtis, two-stage flight. He flew on a CTI short burn motor and an Aerotech, I think it was an M685. Yeah, I think I mentioned that here. In 2007, Aerotech introduced the M750W and later the N1000W. Those are both 98 millimeter RMS moon burners. And then we released the M650 and M685 75 millimeter moon burners about the same time. So that's what you're seeing here in this picture was a M685 upper stage. And all these motors are capable of extreme altitude performance due to their long burn times. The N1000 was capable of over 40,000 feet single stage. I believe Ken Biba flew one to that altitude. And the M685 was capable of flights over 150,000 feet in a two-stage rocket using high-thrust N-class boosters. Other companies that have produced long-burn moon-burning motors over the years include Vulcan Systems, CTI, and Ellis Mountain. Kind of trying to wrap up these high-power reloadables, we go to 2008. Aerotech introduced an L339N, which was a 98 millimeter N burner in the RMS 98 2560 single grain casing. That motor burns for about 8 seconds and uses our fastest Warp 9 propellant. And this is the largest N burning motor currently available to a certified flyer. And you see the thrust curve there in the lower right. And the reason it regresses is simply because a nozzle erodes that much over the 8-second burn. And then in 2010, you can tell we're still interested in these long burn motors. We introduced the J99, which was a 54 millimeter N burner in the RMS 54 852 reload case. Burned for 10 seconds and used Warp 9 propellant again. And you can see again, the nozzle throat erosion on a smaller motor. It's going to be, if you're eroding at a specific rate, the area change is going to be higher on a small motor than it is on a large motor. It was discontinued sometime after introduction due to reliability issues, but it was reintroduced in 2020 using a new propellant casting tube that eliminated edge burning and tunneling effects, meaning unexpected increases in surface area during the burn. This new casting tube material is also used on all the newer N burning motors to avoid that problem. Now, kind of going back to the original impetus for these long burning motors, going back to the gliders, in 1993, Aerotech introduced the F-13 and G-12 N burning reloads and the hardware to go with it for the Aerotech Phoenix rocket glider, which is now pretty much only available on eBay. Reloadable versions of the ENDBURNING D7, E6, and a mid-range ePulse E7 and a hardware set were released in 1994. In 2013, Aerotech introduced a 18 millimeter C3 and D2 reloads for the 1820 case, along with a plug-forward closure. And then in 2018, a single-use version of the C3 was certified for the INTERNATS team, and they were using those in competitions for these gliders. And obviously, you can't use. It would be detrimental to use really high thrust motors on gliders because they tend to tear the wings off. So these long burning motors work beautifully. And okay. So in terms of design considerations, if you're looking for designing motors yourself, or what kind of trade-offs are involved in a long burning motor design. Regarding the propellant, for ENDBURNERS, a fast propellant is desired to generate sufficient thrust. For MOONBURNERS, almost any standard propellant can be used. So that's a big attraction on the moon burning side, is that you don't have to have a super fast burning propellant. For the casing, you can use phenolic, fiberglass, or aluminum. Of course, you're going to have, with fiberglass and aluminum, generally you're going to have to be insulated. But typically, long burning motors operate at lower average chamber pressures than center core burning motors, so they don't have to have the safety margins that you would with a high thrust motor. On the nozzle, if you want to use graphite, that in my opinion works the best. Has low throat erosion, but you're going to have high thermal conductivity and other motor components, so you're going to have to allow for that. Now, phenolic nozzles have very low thermal conductivity, but higher throat erosion, especially at higher pressures. For lining the casings, paper actually works pretty well for short burn times, and the phenolic tubes for longer durations. EPDM rubber can also be used, but its fabrication can be more difficult. You can either lay up sheets, or there are some liquid materials that you could apply, but then there's some difficulty in that. On time delays, it is possible, but again, difficult to implement in mass production. But you could, if you're making motors for yourself, you can take all the time you want. So it can be done. There's ways to do it. For igniters, something to keep in mind is long burning motors will typically have a smaller nozzle throat, and igniter insertion and proper placement can be challenging. So at NARCON 2018, I met Joe Barnard, if you know who he is, of BPS Space, who was working on thrust vector control rockets using some very sophisticated flight computers and servo mechanisms. He'd been using 29 millimeter black powder motors like F-15s from Estes for propulsion, but wanted something longer burning and with more total impulse. So I told him we could build some long burn G-class motors for his application. And that was the impetus for developing the modern, recently certified G8, G11, and G12 motors using Super Thunder propellant. So as we started testing these, you can see the initial testing with some of the different propellants generated some very interesting and weird thrust curves. And most of these were not what we were expecting. So we got some that were progressive, some that were regressive, some that had thrust spikes that we may or may not have been looking for. Here's a couple more. We're starting to get a little closer to what we want here. I think Joe really wanted something with a fairly constant thrust. I think the upper right picture there shows one using a form of white lightning propellant. We pretty much ditched that one after a while. It was just, I think it was depositing stuff on the nozzle and changing the throat area. So eventually we settled on modified ENDBURNING geometry and Super Thunder propellant for the new long burn motors. And this formulation has a burn rate in between Blue Thunder and Warp 9. They used a 16th inch wall, 29 millimeter OD fiberglass epoxy case, and a 32nd inch wall phenolic liner. The G8 was a straight end burner. The first G11 and G12 motors had a shallow slot in the aft grain and the aft grain end to provide an initial thrust spike. The G11 and G12 only slightly differed in throat diameter by about 0.005 of an inch. We were basically just trying to dial in the thrust levels. These motors were all triply certified in 2018, but after certification, I don't know why, but maybe they looked at the data later or something, but they didn't pass the 200 and it's actually, I think, 220 degrees centigrade maximum casing temperature spec. No, it is 200 because these are model rocket motors. So the certification was revoked, unfortunately. So you can see the designs of these. One's got a little slot in the end, and I think it had a slightly faster burning version of the propellant. You can see the static test there with the thrust spike and the nice sustained burn. Very nice low erosion due to low pressure, fairly low pressure. And when I say low pressure, I'm talking about roughly 120 to 150 psi. Now, if you don't know what hamster dance is, it's a contest that Tripoli runs. And Tripoli Gerlach actually had been running it for 10 years. And I've flown in it most, I don't know, maybe 8 of them, 7 or 8 of them. But as we were working on the motors for Joe Barnard, I realized that a long burn G or H motor would be ideal for the hamster dance altitude competition. It's held annually during the balls launch at the Black Rock Desert. Started running flight simulations and discovered that the performance of these designs could approach the 15,000-foot altitude ceiling of the contest when used in a very lightweight rocket. So the 29mm H11 and H13 motors were developed for the contest and were flown successfully in 2018 and 2019, achieving 12,096 and 13,219 feet, respectively, in minimum diameter rockets constructed from Quest kit parts. Yeah, model rocket parts. And here's the motor designs. You can see really the only difference was the shape of the core and the length of the grains. Just some pictures from the contest. You can see how small the rocket was. The H13 rocket was essentially the same design, but a couple inches longer. And when you see these things lift off, there's very little smoke, and within a couple of seconds, you don't see them anymore. You just hear them. And kind of in the middle of all this, we got a request for long burn motors from a movie production company or a TV production company. But 32 of the H13 motors were used in an effort to duplicate a British World War II weapon called the Panjandrum, which was for an Adam Savage Science Channel TV show. The device worked pretty well and hit the side of the target it was aimed at. And if you haven't seen that video, you can probably find it. 31 of the 32 motors ignited successfully. There it is, launching off its trailer. So I mentioned a little bit ago, I'm kind of running a little late, sorry, but I was hoping to get done by now, but we just have a few more slides. The thermal issues with these motors, why they were not certified. Again, the initial certification was revoked because of high temperatures. We started trying to change the code revision process, and we demonstrated through testing that higher temperatures of long burn motors using non-metallic casings were not a safety concern, but we ran into some political roadblocks. Steve Shannon recommended that we find a technical solution to the casing temperature problem. I knew this would be a costly option. So we began working on a technical solution to the issue while also pursuing the NFPA code revision effort. So the technical solution involved 3 design changes. We reduced the fiberglass casing wall thickness from a 16th inch to a 32nd of an inch, just like the old Composite Dynamics motors. We increased the phenolic liner wall thickness from a 32nd to a 16th. And we reduced the nozzle OD from 1 inch to 15/16 inch to fit inside the liner. These changes did not affect the propellant grain diameter or the nozzle throat diameter, so the motor ballistic performance was unchanged. The motor weights were reduced by a few grams because phenolic tubing is less dense than fiberglass. So you're just replacing, some of the material was just replaced by a lighter material. But however, it did reduce the casing temperature to the point where the G8, G12, and H13 motors passed the NFPA casing temperature requirements and were all recently certified. So the H-13 is available. The G-8 and the G-12 will be available later this year, actually, to people who want to use them. And for Hamster Dance 10, which was supposed to happen last year, contest organizer Tom Blazanin decided that the altitude ceiling would be lifted, so we were only limited by how high an altitude one could achieve with a 5-pound liftoff weight, non-metallic rocket motor. So I started working on 38 54mm motor designs and simulated performance on Open Rocket. This effort resulted in the design of the 54mm K76WN boost sustain motor, which was recently certified. But since HD10, Hamster Dance 10 was canceled due to COVID, I decided to fly my HD10 entry as an exhibition at the Airfest launch in Argonia, Kansas last September. This motor used a core burning Bates grain of White Lightning propellant and an end burning grain of Warp 9, kind of like the I-59 38mm reload. Total burn time of 20 seconds. The rocket, which I called Hamster Riots in Argonia, flew a bit squirrely, but it still reached an altitude of 20,112 feet, according to the Telemetrum flight computer, which was very close to the simulation. And the experience taught me the importance of accurate fin shaping and alignment on supersonic rockets, because unfortunately this thing went supersonic for a short time, and the use of 3 versus 4 fins to avoid coning. But it was recovered intact and undamaged about 2.4 miles away with help from the Telemetrum and the GPS tracker. So kind of to wrap this up, we're going to look at three different comparisons, low thrust versus high thrust. And these aren't absolutely identical comparisons, but you get the idea. So G12 versus G80, similar total impulse, big difference in altitude. G80 short burn motor, 5,800 in this particular rocket, 5,858 feet, with the G12 over 10,000 feet, 10,500 feet. Let's look at the H motors. And again, this is kind of like the Hamster Dance thing, which is what this was. An H135, which is a certified H motor, 8,296 feet, but with an H14 or H13, over 13,000 feet. And with a larger rocket, let's compare a K550 to the K76, a roughly, what, 2-point-something second burn versus a 20-second burn motor, 13,800 feet with the K550, 20,700 feet with the K76. That's actually was the Hamster Dance 10 design there. So with future, what are we going to do in the future here? Hamster Dance 10 was postponed at least 1 year, so it got me to thinking about even greater possible performance. In other words, beyond the K76 idea. But it turns out that when you start running the simulations and kicking in even longer burn time motors and really pushing it to the limit, altitudes approaching 60,000 and actually more than 60,000 feet may be possible with a 5-pound liftoff weight rocket. So it all comes down to how long a thrust duration is technically achievable and if the rocket can fly straight enough during the burn. So I've been personally working on some full K and low to mid L long burn motors that may be capable of reaching something in that range. And there's other contestants doing the same thing, and they may put me and the other participants to shame because they're putting more time into this than I am. I actually hope somebody else wins the contest, because one of the benefits to winning this contest is you're prefect of the Tripoli Gerlach. So it's time to pass the hat on that one, I think. And just looking at a simulation of a super high performance long burn motor. This is an L155 simulated altitude, 56,600 feet. And unfortunately, you start getting up to this performance range, you're getting up to almost 3,000 feet a second. So you could potentially get some aerodynamic heating. 20-second burn time and almost a minute to apogee. And this is just, remember, this is like a 2-inch diameter, 2 1/8-inch diameter rocket that's only a little over 2 feet long. So pretty incredible performance from small rockets with long burn. And we'll now have a question and answer. So let me see if I can escape this and go back to.
Yeah, Gary, I've got them up
Yeah.
here. I can read them off for you.
Okay, let me just switch over here. All right, go ahead.
Okay. Let's see. The first question we have. I'll start at the bottom and make my way back up. All right. Osvaldo was asking about the articles. I think somebody posted the link. I guess those maybe in the comments, but I guess he's asking where are those articles that you were talking about from the original magazines.
Yeah, it's I will find them quickly for you. If you go to rocketmotorparts.com, go down to where it says store links. I think it's under, yeah, it's under documents. Yeah, on the documents page, it'll say, oh, wait a minute. Okay, where is it? Oh yeah, there it is, under technical reports, where it says Motors of the 80s, part 1, 2, and 3. Those are where the articles are.
Excellent. Thank you, sir. Appreciate that.
And you want to, some of those other articles are technical reports are really great. You know, people should read, especially Dan Meyer's report on delivered specific impulse. Excellent report. Still valid.
Thanks, sir.
Okay.
All right. Yep. Next question. This is actually, I was curious about this. Do moon burning designs erode the nozzles faster than a core end burning design? Like any differences between graphite, phenolic, and ceramic that affect from that type of motor?
Well, it's a balancing act, right? You've got a longer duration, so in theory you're going to erode it more, but generally speaking, those motors are going to run at lower pressures, especially near the end of the burn. So it all depends on the exact configuration. I've seen motors that had no difference in erosion, just because you're balancing those two things.
Gotcha. Okay. All right. Next question comes from Peter, and he's asking, how far into the plug of an H13 can I drill and tap for an eye bolt? How about this for a technical support question? Also, will there be an eye bolt impregnated version like the thrust string less version?
Well, I don't know. You could drill into the epoxy. I mean, in theory, I'm not saying we recommend doing that. I think it's about 3/8 of an inch thick. But you know, yes, if there was a demand for eye bolts in those, we could put that in there, or we could put a little loop of Kevlar or something in there. Yeah, I haven't had. That's the first time I've heard of somebody asking for that.
Well, that's typical for Peter because we've already banned him from 2 other sessions. So I'll be happy to ban him from this one too, if you'd like.
No, it's okay. It's like I said. I mean, there's actually a drawing of those motors, of all the DMS motors, are on the RCS site. Again, if you poke around there, you'll see drawings of all the motors, so you can kind of infer it from that.
Very good. All right, thanks, sir. Let's see. Next question. Ben Murdoch. Do you have resources you could recommend for learning about solid motor design and manufacturing, and any software you use for the design process?
Well, I guess one of the best resources is Dr. Terry McCreary's book on experimental composite propellant. And let's see, what was the other question?
Software. Any software you can use.
Well, yeah, we use a proprietary software that my ex-partner produced, but you know, you've got BurnSim, so I would use that. A lot of people use BurnSim.
I know there is a new one that's out there called Open Motor, I think.
Open Motor, yeah.
Yeah.
I haven't used that myself.
Yeah, neither have I. Okay. That's that one. Peter again. Okay. Thanks, Peter. Another good question. For EPDM rubber sheets, how do you bond them to themselves? I've had some luck with cyanoacrylic, never say that word, but it seems to be one of the few things that work.
Okay. I'm going to speak in terms of without personal knowledge, but this is just my brain trying to put things together, because when we've used EPDM, it's been like not a pre-polymer, but like a partly cured material that we wind on mandrels and then heat cure it. So there's nothing used to bond it. But I would try. I know that you can get EPDM like roofing compound. that, you know, you could probably use as an adhesive. That'd be my guess.
Gotcha. Cool.
Just apply it as a bonding agent.
Very good. All right. Let's see. This one is from Mateo. He has a question. Any tips or tricks for teams competing in Amsterdam this year with experimental motors?
Of course. I would say, first of all, show up and don't Cato. Right there, that'll get you a 50% chance of winning. Because out of 17 entries last year, only 2 qualified flights. I'm not kidding.
Oh, yeah.
There's that. I would just, you know, I think everybody is going to be on a high game this year. So, you know, maybe just build something that works and fly it, and then observe what everybody else is doing. For if this is the first time you're coming out to the contest.
Gotcha. Cool. All right. Diego's question. What are your thoughts on NACA's SRM simulator?
I'm actually not familiar with it.
Yeah, neither am I.
Sorry. Yeah, I'm familiar with BurnSim, and I'm familiar with the software we use.
Okay, that's all the questions that we have at this point. If you've posted a question inside of, oh, it looks like somebody posted a image. I'm looking in the chat section now. It looks like we have a couple of different comments in there, and I think somebody put the link to the RCS store so that they can hunt down those documents.
Yeah.
Let's see. But that's it. Okay, guys, we're at right on scheduled end time. So I want to thank Gary. Thank you, sir, so very much. Not only for being here and helping and teaching all about the history and designs of these, but thank you for everything you've done for the hobby. Thank you for everything you've done for high power rocketry. Can't be expressed enough that, you know, they start talking about high power rocketry legends, and you've got to be at the top of the list. So absolutely.
Well, I appreciate that, Andy, and thanks for all you do, because you do a lot too.
Well, I love working with the students, and the students, you know, make this event what it is, and having as many of them here just drives me crazy. So anyways, thank you, Gary, and at some point I think I'm going to LDRS. I'm hoping you're going to be there as well, so maybe we can meet again.
Well, I was going to make one more comment, and that is, if I encourage people to come to LDRS this year, because this is the first year we're having the Tripoli Technical Conference and Summit. It's called Trade Tech. We've got 12 great presenters, and I think it's going to be very interesting, and I hope it continues going forward, because, you know, it's all about sharing the information and growing the hobby and the education of it.
Outstanding. Looking forward to it very much. Thank you again, sir. Thank you, everybody. Have a wonderful day. And
everybody have a good one. Thanks. Bye.